Section: Introduction. In this section, we introduce the concept of state-of-the-art large language models, LLMs, like Gemini and GPT-4, which are typically developed through three main stages. Initially, we pre-train these models on extensive datasets, focusing on predicting the next word in a sequence. Following this, we fine-tune the pre-trained models to better follow instructions through a process known as supervised fine-tuning, SFT. Finally, we enhance the model's output quality using reinforcement learning from human feedback, RLHF. This RLHF phase usually involves creating a reward model that reflects human preferences and then adjusting the LLM to maximize the predicted rewards using reinforcement learning techniques. We recognize that fine-tuning LLMs with reinforcement learning presents challenges. For instance, it can lead to the model forgetting previously learned information, and flaws in the reward model can result in unintended behaviors, often referred to as reward hacking. To address these issues, we typically employ policy gradient methods that include regularization to maintain alignment with the SFT policy. These reinforcement learning algorithms aim to find optimal policies that achieve high rewards while minimizing the risk of misalignment. In practice, we often use a straightforward method called best-of-n sampling to enhance the quality of the model's outputs. This approach involves generating multiple candidate outputs from the reference model and selecting the one that receives the highest reward from the reward model. While this method effectively balances reward and computational efficiency, it does increase the computational cost significantly. To tackle the limitations of best-of-n sampling, we propose a new algorithm called BOND, which stands for best-of-n distillation. Our innovative approach allows us to achieve the strong performance of best-of-n sampling while only requiring a single output during inference. The core idea behind BOND is to frame the alignment of the policy as a problem of matching distributions, where we fine-tune the policy to replicate the distribution of outputs generated by the best-of-n method. We begin by deriving a mathematical expression for the best-of-n distribution, which enables us to explore and optimize various divergence metrics. We demonstrate how to minimize the forward divergence using samples from the best-of-n strategy, leading to a standard imitation learning setup. Additionally, we show how to minimize the backward divergence, resulting in a new form of advantage that does not rely on the reward scale. We also propose minimizing a combination of both forward and backward divergences, known as Jeffreys divergence, which captures the strengths of both methods. To enhance performance while reducing the number of samples needed, we introduce an iterative bond approach that involves distilling the best-of-n outputs from a moving anchor policy. Building on these concepts, we present J-Bond, a new, stable, efficient, and practical RLHF algorithm designed to align LLMs effectively. In our experiments, we first validate the effectiveness of BOND and our design choices using the XSUM task for abstractive summarization. We then apply J-Bond to align the policies of the Gemma model. Our findings indicate that J-Bond not only improves the trade-off between reward and divergence compared to standard reinforcement learning algorithms but also enhances performance on academic benchmarks and in direct comparisons with open-source models like Mixtral. We focus on a LLM based on the transformer architecture, defining a policy that generates sequences of tokens from a given prompt. With access to a pre-trained and typically supervised fine-tuned reference policy, we aim to further align it with human preferences. Throughout the paper, we assume we have a reward model that reflects these preferences. In standard RLHF, most algorithms optimize a combination of expected rewards and a divergence measure between the current and reference policies, with a regularization factor to keep the policy close to its initial state. This regularization helps prevent forgetting and reward hacking. We find that simple methods often yield the best results, such as using reinforce with a sample baseline for variance reduction, which outperforms more complex approaches like PPO. Best-of-n serves as a complementary strategy for alignment, focusing on inference time adjustments rather than fine-tuning the model's weights. While it has been shown to be efficient in terms of reward and divergence trade-offs, it does come with a higher computational cost, as generating multiple outputs is more resource-intensive. Motivated by these insights, we introduce Bond, aiming to distill the best of N strategy into the policy, allowing it to achieve similar performance while only requiring a single output during inference. We will outline our overall approach in the following section. Section Summary. In this section, we describe the training process of large language models, LLMs, which typically involves pre-training, supervised fine-tuning, and reinforcement learning from human feedback, RLHF, to enhance generation quality. We introduce our novel algorithm, Bond, Best of N Distillation, which aims to achieve the performance of the best of N sampling method while only requiring a single sample at inference time, thereby improving efficiency without sacrificing quality. Section: The Bond Approach. In this section, we outline the Bond approach, which consists of two primary steps. First, we derive a clear analytical expression for the best of N distribution. Next, we use this expression to frame our problem as one of distribution matching, meaning we aim to adjust our policy to align more closely with the best of N distribution. We also highlight important connections between Bond and standard reinforcement learning from human feedback, RLHF. Now, let's discuss the best of N distribution. Here, we derive the precise analytical distribution for best of N sampling and examine its characteristics. To simplify our analysis, we omit the context from our notation without losing generality and assume that the reward creates a strict ranking among all generations. We can state a key theorem, which we will prove later. For any given generation, we denote the probability that a random generation is strictly worse than this generation, and we also denote the probability that it is not better, including the case where it is equal. The probability that our generation is selected in best of N sampling can be expressed in terms of these probabilities. The theorem provides an intuitive understanding of how best of N sampling works. It effectively reweights the original sampling distribution using specific multiplicative factors. One of these factors corresponds to a penalty that grows exponentially based on the fraction of generations that are worse or equal to the generation we are considering. This means that as this fraction increases, we sample significantly less from poorer generations. The other factor serves as a correction due to potential overlaps among generations and is at most linear in its influence. This correction factor reaches its lowest point for the worst generation, as we need to sample it a specific number of times in a row. Conversely, if the likelihood of individual generations is low but they are still good, this correction factor approaches a value close to 1, indicating that sampling a generation multiple times is unlikely. In cases where the original distribution is continuous, this correction factor remains constant and equal to 1. Moving on to the Bond objective, the analytical description of the best of N distribution allows us to frame Bond as a distribution matching problem. Our goal is to minimize a divergence metric that guides our training policy toward the best of N distribution. There are various divergence metrics available in the literature, and we can use existing techniques to estimate our target distribution from both online and offline samples. We will discuss the selection of appropriate divergences and the resulting Bond algorithms later. Next, we explore the connections between the objectives of standard RLHF and Bond. It is well established that the policy that maximizes the RLHF objective aligns with the best of N sampling distribution when we use a specific Bond reward and a particular regularization strength. The correction factor we mentioned earlier is bounded for all generations, while the other term lies within a defined range. This leads to two significant insights regarding best of N sampling. It can be seen as a solution to a standard RLHF problem with regularization, where the choice of a specific parameter determines the level of regularization. Additionally, it optimizes the expected log reward quantile, which reflects the likelihood that a generation has a higher reward than a random sample from the reference distribution. Due to the nature of logarithmic functions, this approach encourages the model to avoid poor generations rather than simply promoting the generation of good ones. Furthermore, this method is robust to changes in the reward structure since it relies solely on the ranking of generations. We believe that these characteristics make the Bond reward more resilient to reward hacking compared to standard RLHF. The connection to RLHF also informs our proposed approach. If we can calculate the bond reward or the best of n distribution, we can guide our policy toward the best of n distribution through distribution matching. In the following section, we will investigate various algorithms to address the key challenges we face. Section Summary. In this section, we outline the bond approach, which involves deriving the best of n distribution and framing it as a distribution matching problem to guide our policy towards this optimal distribution. We also establish connections between bond and standard RLHF, demonstrating that best of n sampling aligns with the optimal solution of RLHF under specific conditions, potentially enhancing robustness against reward hacking. Section: Bond Challenges and Algorithms. In this section, we address the challenges and algorithms associated with implementing the bond approach. We encounter three main challenges. First, how to estimate the reward quantiles. Second, which divergence metric is the most suitable. And third, how to select the hyperparameter that indicates the number of sample generations in the best of n method. We will discuss and tackle these challenges in the following subsections. When it comes to estimating the quantiles, we face a significant difficulty in determining the distribution of a specific generation. The quantile we are interested in measures how the quality of this generation compares to others when conditioned on the same prompt. A straightforward yet effective method for estimating these quantiles is through Monte Carlo sampling. By sampling a number of generations, we can obtain an empirical estimate, which we found to be quite effective even with a limited sample size. Alternatively, we could explore other methods, such as training a learned quantile model. Next, we consider the choice of divergence metric, which is crucial for the bond approach. Different divergence metrics can lead to very different outcomes. We propose using the Jeffreys divergence as a robust objective for matching distributions. This divergence is essentially a weighted average of the forward and backward divergences. When we fine-tune our policy, the forward divergence encourages generations that are likely under one distribution to also be likely under another, promoting a mode-covering behavior. In contrast, the reverse divergence tends to focus on producing generations that are highly probable according to the reference distribution. While the forward divergence can lead to overly spread-out distributions, the backward divergence can cause issues like policy collapse. Our empirical findings suggest that the Jeffreys divergence combines the strengths of both approaches, leading to better aligned policies. In the context of bond, we aim to minimize the Jeffreys divergence, which we can estimate using samples from both the training policy and the reference policy. For estimating the forward divergence, we can draw samples from the reference distribution and select the best one, treating this as a supervised fine-tuning loss based on the best of n samples. For the backward divergence, we estimate it from the policy samples and their log likelihood under the reference distribution. We demonstrate that the gradient of this estimation aligns with a policy gradient, similar to what is used in standard reinforcement learning with human feedback. In practice, we substitute the true quantile with its estimate, as the correction factor does not significantly impact our results. To reduce variance, we also use a policy gradient baseline, which we calculate as the average return for the other generations in the batch. Consequently, the overall loss for the Jeffreys divergence is a linear combination of a supervised fine-tuning loss and a policy gradient loss. In our experiments, we focus on the abstractive summarization task using a specific supervised fine-tuned policy and a reward model. We run bond with the Jeffreys divergence objective and utilize Monte Carlo samples to estimate quantiles during training. During evaluation, we also use samples to estimate the divergences between the training policy and the reference distribution. Our results confirm our hypothesis. The Jeffreys divergence effectively minimizes both divergences compared to when we only minimize the backward or forward divergences. Additionally, we observe that bond maximizes the quantiles similarly to the mode-seeking approach, while the mode-covering approach lags behind. Section Summary. In this section, we identify three main challenges in implementing the bond approach: estimating reward quantiles, selecting an appropriate divergence metric, and choosing the hyperparameter for sample generations. We propose using Monte Carlo sampling for quantile estimation and recommend the Jeffreys divergence as a robust metric for policy alignment, demonstrating its effectiveness through experiments in the context of the X-sum task. Section: Iterative Bond. In this section, we discuss the iterative bond approach and the challenges associated with selecting the parameter we denote as 1. Choosing this parameter can be tricky for three main reasons. First, similar to standard reinforcement learning from human feedback, RLHF, this parameter acts as a regularization tool. A larger value can enhance performance in subsequent tasks, but if it becomes too large, it may lead to over-optimization of rewards. Second, a larger parameter makes our estimates more sensitive to errors in the estimated quantiles. Third, estimating the forward Kullback-Leibler divergence requires sampling from our distribution, which can be impractical when the parameter is large. To tackle these issues, we propose the iterative bond method. This method is inspired by the observation that sampling the best option from a best of n distribution is equivalent to sampling from the original distribution. More generally, we can think of the best of n operation as a way to sample from a base distribution. This leads us to the core idea of iterative bond. If we can effectively distill the best of n distribution, we can apply this process repeatedly, which is akin to distilling a best of n from the original distribution multiple times. This allows us to set a small parameter and run bond iteratively, acting as an improvement operator. We introduce an auxiliary anchor policy, initialized as the original distribution. We then run bond against this anchor, distilling its best of n version. After a certain number of distillation steps, we update the anchor to reflect the current training policy. We illustrate this overall approach in a figure and summarize it in a pseudocode format. In essence, iterative bond enables us to scale to larger parameters without needing to set them in advance, while also maintaining lower sample complexity and stable optimization. We validate this claim with our experimental results. In our experiments, we replicate the setup from a previous figure, fixing the bond objective and running iterative bond with a moving anchor updated every 1,000 steps. We report the average reward and average log quantile obtained during training, comparing them to a non-iterative bond run. As anticipated, the reward signals for non-iterative bond saturate early, while the iterative bond approach shows continuous improvement in performance. Additionally, we plot the obtained log quantiles against those from the reference policy, demonstrating that iterative bond maintains a similar reward and trade-off while allowing for a gradual shift away from the original distribution. Next, we introduce J-bond, a practical bond algorithm inspired by our previous findings. We outline its main components and summarize it in a pseudocode format. J-bond follows the iterative bond template, fine-tuning the policy to iteratively distill the best of two version of a moving anchor, initialized as the original distribution. The name J-bond refers to its use of Jeffreys divergence as the objective for distribution matching. J-bond is designed to have minimal sample complexity. For each prompt in a batch, it generates a small number of samples from the policy and more from the anchor. While more samples can improve divergence estimation, we focus on a practical approach that works with fewer samples, as autoregressive sampling can be a bottleneck in online RLHF. We use the policy and anchor samples to create a rough estimate of the forward and backward KL components of the Jeffreys divergence. To minimize the forward KL, we perform supervised fine-tuning on the best of the two anchor samples. For the backward KL, we employ a policy gradient style loss, adjusting the reward to account for the limited anchor samples. Specifically, if a generated sample performs worse than both anchor samples, it receives a negative reward. Otherwise, it gets no reward. An important aspect of J-bond is the use of an exponential moving average, EMMA, for the anchor. Instead of updating the anchor periodically, we adjust its weights at each fine-tuning step based on a moving average of the policy weights. This averaging process has been shown to enhance training stability and improve the overall reward and KL trade-off in J-bond. We provide further analysis of this in our experiments. Additionally, we introduce extra regularization to keep the policy close to the moving anchor, controlled by a tunable hyperparameter. Section Summary. In this section, we introduce the iterative bond approach to address challenges in selecting the parameter number 1, allowing for improved performance and reduced sample complexity by recursively distilling a best of n distribution. We also present J-bond, a practical algorithm that minimizes Jeffreys divergence with minimal sample complexity, utilizing an exponential moving average anchor for enhanced training stability and an additional KL regularization term to maintain proximity to the moving anchor. Section: Experiments. In this section, we test J-bond on relevant use cases with several main objectives. First, we analyze and highlight key features of J-bond, such as the advantages of using the exponential moving average (EMMA) anchor, the impact of anchor speed, and the additional Kullback-Leibler (KL) regularization. Next, we compare J-bond to traditional reinforcement learning from human feedback (RLHF) methods using the reinforce algorithm, showing its effectiveness and superior performance. For our setup, we focus on the GEMMA models, specifically the 2B and 7B versions, which we aim to fine-tune into more effective conversational agents. We utilize a set of 143 conversational prompts, a reference policy that has been previously fine-tuned on similar prompts, and a large reward model that has been trained beforehand. We employ a batch size of 128 and use the Atom optimizer with a specific learning rate and 100 warm-up steps. For the Jeffreys divergence objective, we set a particular value. We investigate the benefits of using an EMA moving anchor compared to a periodically updated anchor. To do this, we run J-bond with a specific EMMA coefficient on the GEMMA 7B model and compare it to a version where the anchor is updated every 145 steps. We present the average reward of the policy during training, the KL divergence from the reference policy, and the resulting trade-off between reward and KL for both runs. Both configurations show a similar increase in reward, which is expected since the EMMA with the chosen coefficient corresponds to an update period of about 50 steps. However, J-bond with the EMMA anchor shows a significantly lower increase in KL divergence, leading to a better reward to KL trade-off. Next, we illustrate the effects of the anchor mixing parameter and the benefits of the additional regularization parameter. We run J-bond with different values for these parameters on the GEMMA 2B model. Our findings indicate that a larger mixing parameter, meaning a faster moving anchor, results in a quicker increase in reward, as one might intuitively expect. We also fix one parameter and test various strengths of regularization. The results show that stronger regularization leads to more constrained policy updates, causing the policy to move away from the reference more slowly. Importantly, we find that this regularization positively impacts the reward to regularization trade-off. We then compare J-bond against standard RLHF algorithms that aim to maximize a specific regularized objective. To optimize this objective, we use reinforce with 2 policy samples per prompt and a leave one out baseline for policy gradient advantages. For J-bond, we set the anchor mixing coefficient to a specific value. Our comparison reveals that reinforce is sensitive to the regularization coefficient. As the regularization increases, the reward achieved by reinforce decreases, along with its KL divergence from the reference policy. This highlights a significant advantage of J-bond, which does not require a fixed regularization level and continuously improves the reward while maintaining a stable and linear increase in KL divergence. Additionally, we show that J-bond achieves a better reward to KL trade-off than all reinforce baselines. We also applied J-bond to fine-tune open-weight models like GEMMA 1.1, 2B and 7B, recurrent GEMMA, 2B and 9B, and code GEMMA 1.1, resulting in competitive performance. For instance, the GEMMA 1.1 IT7B model outperforms the Mistral 7B version 0.2 instruct model in both safety and instruction adherence. In the related work section, we note that best of n was introduced as a simple yet costly method for optimizing language generation against a reward function. Subsequent research has refined the analytical form for KL divergence against the reference policy, provided estimators for average best of n rewards, and established connections with regularized reinforcement learning. Various strategies for improving alignment through best of n have been explored in the literature, including supervised fine-tuning on best of n data and preference optimization methods. We also mention that the EMMA of policy as a reference in regularization, which we utilize in JBond, is gaining popularity. While most alignment methods use a static anchor, dynamic anchors enhance the flexibility of the policy space, although they must balance update speed to avoid hindering optimization or stability. Finally, we discuss how Bond focuses on investing more resources during training to keep computational demands low during inference, a factor often overlooked in traditional scaling laws. Bond incorporates principles of iterated amplification, which involves generating multiple outputs, comparing their rewards, and using this information to iteratively enhance policy performance. In this context, Bond complements previous methods that scaled post-training by training multiple reward models and policies.